And today I am the speaker, so I think you already read this introduction. I'm Hiroaki Nishikawa with NIA. I finished PhD a long time ago, and I'm also known as Katate Masaska. And Cosmo asked me what this pseudonym means, it's actually, it means in Japanese, it means part-time writer. So I write only when I have time. So if you ask me volume 2 when it's coming, I just don't have time right now. So. Anyway, thank you very much for coming. And from time to time, I need to check if people are coming in. Okay. So today's topic is U-MUSCL and FSR, flux and solution reconstruction schemes, designing unstructured grid schemes for smooth hexahedral grids. But what I really, somebody is coming in, and I need to let them. What I really want to talk about today is this, yarigai. It's a Japanese word meaning worth doing or sense of fulfillment, satisfaction that you're doing is something valuable. You can find many examples in Japan, but I found this one example by a blog article by a farmer. The farmer received a letter. He showed the letter here. The letter says that we love your spinach. The spinach you make, and it's amazingly sweet and delicious. And when the farmer receives this letter, he's so happy that he got to find this yarigai. Okay, this is worth doing. And I think it's the same in CFD. Whether you're a researcher or CFD users, you need to have a yarigai to get motivated. And from time to time, I receive emails saying your algorithm, I tried your algorithm and it works great. And that gives me yarigai. Okay, and in this talk, particularly, I want to talk about this smooth hexamesh. Is it worth doing? And there are people who try to generate smooth hexamesh for unstructured grid CFD solvers. Okay. And they must have yarigai in their jobs because there are good reasons that the grid is better to be smooth and hexahedral. Better accuracy, robustness with smooth, non-skewed hexa, and the central schemes can be stable and useful on a smooth hexagrid, and so on. And in this talk, I'd like to discuss another reason that the grid is better to be as smooth and hexahedral as possible, like those in the pictures. So you have more yarigai for generating smooth hexamesh. And I'm talking about unstructured grid solvers. Okay, so a typical unstructured grid scheme in practical CFD codes will look like this. For conservation law, you have time derivative and the flux balance. This can be node-centered, so the flux is at the edge midpoint, or cell-centered. The flux is at the phase center, and then source cell. And numerical flux usually has two parts: the central part and dissipation part. Okay, and everything is computed based on the left state and right state, linearly reconstructed from the node to the edge midpoint, or from cell center to the phase center. And the gradients are typically computed by least squares. So you have some coefficient and you go over the neighbors. And here's the question. Can we design an unstructured grid scheme such that it becomes a high order accurate scheme if the grid is smooth hexa, so that it's worth generating smooth hex grids? That's the question. And such scheme will serve as a low dissipation scheme, even if the grid is not really smooth and hexa. And actually, some decades ago, already people have thought about this. And in 2005, in this famous paper, the Burg generalized a Van Leeuwen's kappa scheme in this form. This is an alternative form, but this is an interesting form. The solution average over the edge, arithmetic average, and here's the linear reconstruction, in a typical scheme. This is a weighted average, and the weight is kappa. Okay, so this is the second order accurate scheme over this edge, if the flux point is edge midpoint. But I have to point out a little bit about this. If you apply this cell-centered, the edge midpoint phase point is not necessarily halfway between two cell-centered. So you have to modify this to preserve second order accuracy. And also, I have to mention that 5 years earlier in France, the Devier and the Dervue, they proposed a beta scheme. It's very similar. It's just a different definition of the gradient. And that this beta and kappa are related. Kappa equals 1 minus 2 beta. And I found it very interesting. The special value kappa 1/3 corresponds to beta 1/3, the same value. So anyway, if the grid happens to be regular, like this, down here, right, and then the gradient becomes the central difference gradient, and the scheme reduces to Van-Leeuwen's kappa scheme. This is a Van-Leeuwen's kappa scheme, also proposed about 4 decades ago, and which leads to third-order accuracy advection scheme with kappa 1/3. Okay, so as desired, the U-MUSCL is an unstructured grid scheme that reduces to a high-order scheme if the grid happens to be regular hexa. But I have the question, really? Because from this paper, there have been a lot of confusions. Because Burg demonstrated in third-order accuracy in a 1D test with kappa 1/2, not 1/3. Shouldn't it be kappa 1/3? And also Burg said in this paper, the third-order accuracy is lost in multi-dimension. And but in reality, the third-order accuracy has been observed by many people with kappa 1/3 in multi-dimension for linear problems. So here, kappa 1/3, but in 1D, kappa 1/2. It's a mystery. And this is just two of many confusions, and there are contradictory statements also in other papers, like muscle cannot be third order for nonlinear systems, and even in famous CFD textbooks. So I spent some time trying to resolve these confusions and published a series of papers. The first paper is about truncation error analysis of a third order muscle scheme. I just wanted to show that the muscle is third order, no question. It's a third order for linear or nonlinear problems. And the second paper, I think this one is interesting title. Quick scheme is a third order finite volume scheme with point value numerical. If this title makes sense to you, you don't need to read this paper. But if it doesn't, probably you should read this paper. And so the muscle and the quick are both finite volume, but the definition of the numerical solutions is different. That's why you have kappa 1/3 and kappa 1/2. And this talk is about basically coming from these three papers. The third one is U-MUSCL can be third order accurate only for linearized schemes problems. If you agree with this statement, I think it's good that you read this paper. And finally, based on these three papers, the fourth one, I finally tried to clarify all the confusions and then identify the most economical scheme, the scheme that can be high order if the grid is regular. And that's the FSR scheme. Those schemes are introduced in this paper. And then we published another paper with Emmett at NASA Langley. We discovered another new scheme. This is an interesting scheme, but it's third order only on regular tape mesh. And some fun 3D results. And finally, the last paper, this is a paper with Bram van Leer. During this work, I had extensive discussions with him online, and we identified 11 cases, 11 pitfalls, how people fail to observe third order accuracy with muscle. I would recommend this paper. So there are three facts. Before I get to the point, I'd like to just state three facts, because these are the important facts that many people miss. Cell average or point value, they differ by second order error. Okay, so if you integrate some smooth function and compute the error, cell average, Taylor expand and integrate, and all the other terms will vanish, and you end up with point value or cell average equals point value plus second order error, and next one is fourth order. So for second order, it probably doesn't matter whether your solution is point value or cell average. But if you're talking about third or higher order, this is very important. And the same relationship can be applied to the differential equations. If you plug this differential equation into this relationship, you find that the integral form or cell averaged form, this is a typical form used for finite volume, is equal to differential form plus second order error. So when you do truncation error analysis, you need to know which differential form or integral form, which form your discretization is approximating. Otherwise, you get a wrong truncation error, the leading error. The second order error will always come up. And third fact is a kappa scheme. If kappa scheme is applied to cell averages, if you have a cell average solution and you apply kappa scheme to do a reconstruction of the face, then this kappa scheme will exactly recover the point value at the face from cell averages at kappa equals 1/3. Okay. And if kappa scheme is applied to point values, now you have point value solutions. And then this kappa scheme will recover point value at the face exactly for quadratic function with kappa equals one half. And this is actually true on all three grids. If this gradient is computed by quadratic method on any mesh in 2D, 3D, you recover exactly quadratic function at this halfway between two data points. That's very interesting. Okay. So here's U-MUSCL scheme in 1D. Here's the flux balance, and the flux is computed with U-MUSCL reconstructed solution left and right. Okay, it's easy to implement. It will look like this. Okay, so here is the code. I would say this is U-MUSCL. Okay, so left state and right state and compute the flux. And then the flux is distributed to the right and the left and compute the residual. And once you compute the residual, here's the source term, and then you update the solution. Now this can be considered as one stage of the Runge-Kutta multi-stage schemes. Okay, now suppose you get third-order accuracy with this code. Then it's still not clear what the scheme really is. To understand it completely, we must ask two questions. Do you integrate the source term or evaluate it at the point? And is your numerical solution a set average or point value? Because there are different ways you can achieve third-order accuracy with this code, depending on how you interpret your solution and the source term. And if your answer is, okay, I integrate the source term and my solution is set average, then this code is a finite volume scheme. It approximates this set average form because you integrate the source term and your solution is set average. Right? So you have a data, set average data, and in the reconstruction, you have to reconstruct the solution at the face so that you can compute the flux. And then your scheme is, U-MUSCL scheme is a muscle scheme of van Leer. And the truncation error is derived as detail is in this paper. But this residual, the U-MUSCL, and then leading term is the set average form, okay, not the differential form. That's a common mistake. The leading term is an integral form. And then the error is, now this second order error has this factor 3 kappa minus 1. So, and this is for nonlinear equation. Okay, so the flux derivative, Jacobian, appear here. So when kappa is 1/3, now this is a third order accuracy scheme. So there is no doubt that MUSCL is a third order with kappa 1/3 for both linear and nonlinear equations. No doubt. If any paper says only for linear, that's wrong. It's likely that this leading term is a differential form. That's not what the finite volume scheme approximates. Okay. The answer is, I integrate the source term, but my solution is a point value. So you have a finite volume, again, at the same discretization with the source term integrated, but your numerical solutions are point values. But still, you need a point value at the face to compute the numerical flux. So now it's not a reconstruction, it's an interpolation. And this scheme is a quick scheme of Leonardo. Again, this is proposed in 1979. And the truncation error, you can derive it by expanding the solutions and in this form. Again, the leading term is a finite volume, and the second order error term has this factor, 2 kappa minus 1. So kappa 1/2, and then you achieve third order accuracy. Okay. So, but only for steady problems. You know why? Because the time derivative is a time derivative of the set average. But what you are updating is point value solution. So you commit second order error here when you do a unsteady problem. I mean, you can correct it, but I'm talking about that particular code. If you have that code, with this, you cannot get a high order for unsteady. And my understanding is Burg's 1D result was actually obtained with source terms integrated because he actually writes that the source with the integrated source terms. And then he doesn't write what the numerical solution is, but he says the third order accuracy obtained with kappa 1/2. So I think it's likely that his 1D scheme is a quick scheme. And this quick type unstructured-grid schemes have been developed by deconvoluting this time derivative into a point value solution derivatives. That is called the deconvoluted finite volume by Leonardo. And also NASA's Vulcan CFD code has this structure. It's a finite volume scheme, but with point value solution. And they achieve third order accuracy. Okay. And I think this is the most popular answer. I don't integrate the source term, and my solution is point value. Then that code must be approximated in this differential form, because source term is a point value. Okay. And you have a point value solution at the cell center, and then your scheme is approximation to the differential form that can be thoroughly accurate only for linear problems. Okay. So if you derive the solution from equation error, now the leading term is differential. And then you have second order error. Now you have, there is a factor 3 coupled minus 1, but there are other factors here. FUU, that's a second derivative of the flux with respect to the solution, third derivative. So by taking couple 1/3, you can only eliminate just one term. But these extra terms will vanish if the flux is a linear function. So that's why you get thorough accuracy only for linear problems. And but this is a good option because this is the only option that U-MUSCL can be thorough in 2D and 3D if the grid is Cartesian. Because each flux bounds approximates the flux derivative fx or fy or gy to thorough accuracy. And if you add these two, they independently approximate them to third order. So if the grid is Cartesian, you automatically get third order. That's what people observe. You know? And it's not easy for mass and quick because they are finite volume. In multi-dimension, you have to integrate the flux over the phase, even for Cartesian. So one point flux is not enough. And here's the interesting paper by Tamaki and Imamura. They developed some correction term to the flux so that you can achieve fourth order accuracy in the Cartesian mesh. I just don't know how to extend this to an unstructured grid. Okay. So U-MUSCL can be third order accurate as as a muscle, but it's only 1D if your solution is set average and if you approximate set average finite volume, or quick if your solution is point value, but in this case, your kappa must be 1/2. And also for steady, just for steady. And this is the most promising option, the finite difference, kappa 1/3, because it's third order 1D, 2D, 3D, but only for linear problem. So now, you know what I wanted to do. I wanted to achieve third order accuracy for nonlinear problems. Oh, okay. So confusion's resolved. So Burg demonstrated third order in 1D, kappa 1/2. I think that's a quick scheme. And the Burg says third order is lost in multi-dimension, but I don't think that's true. It can be third order on Cartesian mesh with the kappa 1/3, but only for linear problems. For other confusions, you can look at the papers, but I focus on this, how to achieve third order accuracy for nonlinear problems. And the idea goes back to 1989. I think in the structured grid world, everybody knows this. And this is very interesting identity proposed by Xu and Osha. So if you consider a function h, whose set average is a point value flux f, okay? So if you have a point value flux at the cell center, you consider these as set averages of some function h, okay? Then this is a simple mathematical manipulation. If you take the derivative of the set average, you take this difference over the left face and right face. And this is exact relationship. So if you have a differential form, you can replace this df dx by this conservative flux bands. And this is exact. So to achieve high order accuracy, we need to reconstruct h from its set average is f. So it looks like this. You have you actually have a point value, but they are set average of some smooth function h. So now you have to reconstruct this point value of h at the face from its set averages. And that's exactly what this kappa scheme does. I use theta here instead to distinguish it from solution reconstruction. But when theta equals 1/3, that this is exactly what we need. Set averages to a point value. So this is the flux solution reconstruction scheme. It's very simple. You have a U-MUSCL scheme with solution reconstruction, and you still keep this solution reconstruction to compute the dissipation, but the flux average term, they must be computed by the flux reconstruction. So you have to do solution reconstruction and the flux reconstruction. That's why it's called FSR. And I don't use muscle. I try to avoid it because it's not a muscle scheme. Muscle means set average and finite volume. This is a finite difference scheme with point value solutions. Okay. And it's nice to have a free parameter kappa. And because this jump, UR minus UL, if you take the difference of these reconstructions, you find that the leading term is already third order for any kappa. So it doesn't affect your third order accuracy. And if you want to know, you apply linear flux to this flux, this U-MUSCL. So the solution reconstruction applied to the linear flux, you can rearrange this equation into these flux values. So if the flux is linear, the solution reconstruction is actually equivalent to flux reconstruction. That's why you get third order accuracy for linear problems. For nonlinear, it doesn't work. Okay. Third order U-MUSCL and FSR. So in 1D, muscle or quick you can use, but we are interested in multi-dimension, 2D and 3D. So this FSR scheme is the only option that we can achieve higher order in 2D and 3D. But of course, the grid has to be smooth and hexa. And so this is what we wanted. So FSR scheme is an unstructured grid scheme that reduces to a third order scheme if the grid happens to be Cartesian, and theta 1/3 and for any kappa. And if you already have a U-MUSCL, all you have to do is to add this flux reconstruction. Okay. And I'm sure any flux function can be written in this form. And you can identify which is the dissipation. And you know which flux value has to be reconstructed. So this is what we wanted, and this will motivate us to generate smooth hexa, more yarigai. But if you can do third order, of course you want to go fourth and fifth order, right? Oh, by the way, you can ask questions at any time, please. Fourth order, yeah, it's always somebody had already done. Yeah. And in this case, Young and Muscle, 2016, they proposed fourth order U-MUSCL. So what they did is they computed second derivatives of the solutions, and then they added extra term to U-MUSCL scheme. This is a cubic term, and this cubic term is computed by using gradient difference and the second derivative and their difference. So it's cubic, but you don't need third order derivatives. You only need the second derivatives here. To compute second derivatives, they use just the same least square method. So first you compute gradient by using least squares. And typically in 1D, you give central difference approximation to the gradient. And then you apply the same algorithm to the gradient already computed here. And then you end up with this typical 2H Laplacian. So it's a second derivative having one point skipped. So you have 2H space here. And 2H Laplacian is considered as a bad approximation in diffusion schemes. But in this case, this is very important. It's this with 2H Laplacian, it brings more points, more neighbor into the residual stencil. That's how you can achieve high order without directly accessing those far neighbors. I think this is a very interesting idea. So it extends stencil as required by fourth order, and each step requires only access to the neighbors. So it's easy to implement in parallel. You don't need to modify anything, just use the neighbor value. And step by step, you compute gradient and then second derivatives. But again, if you evaluate the flux with the reconstructed solution, it's high order only for linear problems. So you have to do reconstruction for the flux. But it's easy in this case. To achieve genuine fourth order accuracy, we only need to perform the flux reconstruction with theta 1/3, just like third order scheme. Because when you look at the truncation error of this flux balance, the flux average term will generate even order errors, and the dissipation, the solution jump, will generate odd order errors. So, okay. So if you take theta 1/3, this will vanish. And if you take kappa equals kappa 3 to be 1 minus kappa, the third order error will vanish. And then this fourth order error will remain. I mean, you don't need to eliminate this. So So for third order and fourth order, you keep the same flux reconstruction. And how about fifth order? Of course, we can do it by adding extra term in the flux reconstruction. The second derivative of the fluxes, and then you can now have two parameters here, and the theta is 1/3 from here, and then you can eliminate this by taking theta 3 to be -8/15. So you can achieve fifth order accuracy. So these are flux solution reconstruction schemes. Third order, you only need a flux gradient, and fourth order, you need to compute second derivative of the solution, and fifth order, you need to compute second derivative of the fluxes. These are probably okay for structured grid, but for unstructured grid, to implement these schemes, we must compute the gradient of the flux, X flux, Y flux, Z flux, and then second derivatives of these fluxes. And that's a lot of quantities. So it can be very expensive, and I wanted to avoid it. So that leads to this efficient version of FSR. We call it CFSR and QFSR. And these are the schemes currently implemented in Fund 3D. Okay. How to avoid flux reconstruction? The chain rule. We can use chain rule to compute flux derivatives. This flux gradient term, the round means the distance from the cell node to the edge midpoint dotted with this nabla. Okay. And then this computed by flux Jacobian times the solution gradient. And second derivatives can be also written in terms of the solution gradient and solution second derivatives. So by replacing these, I mean, in these flux reconstruction formula, so all flux derivatives are computed with this chain rule. Now you eliminate all these flux derivatives. And this gives you a CFSR3 and 4 and CFSR5. But unfortunately, if you do truncation analysis, the chain rule generates fourth order error in CFSR5. So CFSR5 is actually fourth order accurate because of the chain rule error, and but more accurate than CFSR4. But I just couldn't give up and just try to do see if I can get fifth order. So I did. I tried this idea, the quadratic polynomial reconstruction. So I write this flux, left flux, in terms of the flux at the point, and then the linear term in terms of the solution reconstruction, and quadratic term. And then again, we only need solution and solution gradients and Hessian. We don't need flux derivatives. So that's called what we call QFSR3 and 4. And fifth order accuracy, we require another term, the cubic term, but that's too much. So, and it's very complicated. So I decided to add some extra terms here and there and see if I can eliminate fourth order errors. And when I look at derived fourth order error, it looks like this. It's still very complicated, but I noticed, I mean, if you look at this, this is a flux Jacobian, the fifth order, fourth order, third order. And if the flux is the quadratic function in the solution, these terms will vanish. And then I'm left with these 1, 2, 3 coefficients. And then I have A, B, C, the 3 unknowns. I can solve this equation. And then I found that the A, and B, and C, these values. And so if the flux is a quadratic in solution, you can achieve fifth order with using this flux reconstruction. And it's applicable to Burg's equation and Euler equations using the parameter vector. The flux is a quadratic in this parameter vector. So in this case, when you implement this, you have to do a solution reconstruction and gradient computation in terms of this parameter vector. I think it's an interesting option. So this is a summary of efficient FSR schemes. Third order accurate, which is fourth order with no zero dissipation, and fourth order accurate, these are upwind schemes, and fifth order accurate, and sixth order with no dissipation. Okay. And but of course, this is available, applicable only to the system where the flux is quadratic function in the solution. But now we have more Gary-Guy for generating smooth hexamesh. You can achieve up to fifth order accuracy. Okay. And implicit transport, I just did a quick accuracy verification. I think the vortex will move from here to there. It's a very short distance, but that's sufficient to do this error conversion study. And you can see the from scheme. This is capital 0 second order is up here, and then Young and Harris. This is essentially second order, but it's much more accurate than the capital 0, because here you are computing second derivatives, and the CFSR3 is here. The slope is 3, but it's a little bit less accurate than Young and Harris on a coarse mesh. QFSR3 is more accurate, and the fourth order scheme is here, and the QFSR4 is more accurate. It's here, and then we have this fifth order scheme. And when I did this, the timing, CPU time, CFSR schemes, it's about 2%. I mean, it's just a little bit more expensive than the from scheme. And QFSR, I don't know why, but it has a 20% increase in the computation time. I'm not sure. Looking back, I don't remember why this has more computing time.
This is explicit.
Yes. Yeah. This is explicit time and time step.
And norm computed for pointwise value.
Yes. Yes. Everything is point value. And I did a little bit longer time simulation from 0 to 10, and look at the final solution. Compare U-MUSCL from scheme capital 0, and this is Young and Harris. It's a bit more accurate, but QFSR4, the genuine fourth order is here, and fifth order is even more accurate, very close to exact. And this is a simple 1D Shu Osher problem. On the left, this is the second order scheme with capital 0, and the Young and Harris scheme, and this fourth order U-MUSCL works great. I mean, it's much better resolved. But if you go genuinely fourth order scheming, QFSR4, it does peak, capture more peaks. So, and we tried this with Fun3D, generated this smooth mesh. It's a hexahedral around the cylinder and the wake, and otherwise prismatic. So, and I generated this, I wrote this code myself, and the code is available there. And then we find that this is U-MUSCL kappa 1/2. It's supposed to be more accurate than capital 0, but these fourth order schemes you have much better resolved in the vorticity in the wake. So, okay. So unstructured grid schemes can be designed to become high order if the grid is smooth hexahedral, third or fourth, fifth order FSR. But there are efficient versions, third order, fourth order CFSR and QFSR schemes, and fifth order is possible with the reconstruction in the parameter vector. And these schemes have been demonstrated for relatively simple problems so far, but they are available now, except this fifth order scheme. So I want to say, say to Fun3D users that please try out these schemes. And I hope more results will be presented in the future conferences. And currently, I'm working with Brown boundary on compatible high-order boundary schemes. We already presented one paper about third-order scheme near the boundary at SciTech last year. And I have fourth-order scheme now, and I'm trying to finish this paper. And I'd like to further investigate the limiting procedures for these schemes. And there are edge limiters and the cell limiters, and there are many different options. And the extensions to viscous terms are being done at NASA Langley. And finally, here's my letter to the smooth grid generators. So we love your mesh. It's smooth, amazingly smooth and hexahedral. So thank you very much for your work, and the cheap high-order schemes are waiting for more of your smooth hexahedral. And I hope this will give more yarigai to those people who generate smooth mesh. Thank you. Boris.
Two questions.
Yeah.
First, how stability time step depends on order of accuracy? So is it the same delta t, like or?
Okay, I didn't pay attention too much because I focused on spatial accuracy. So all these tests use just the same small enough time step. It's possible that you need to have smaller time step for higher scheme, of course.
Okay. Another question coming from not smooth hexahedral grid community, so that can you compare, comment on this scheme comparison with third order scheme, like on tetrahedral cuts type of scheme, is it accuracy comparable?
On regular mesh?
Say tetrahedral regular mesh. You don't know.
I didn't compare, but these schemes, the grid must be nice. Grid must be smooth. So if the tetra grid is irregular, there is no question. These schemes are second order.
But I'm thinking about hypothetical situation. You have nicest quadrilateral or hexahedral grid, then you divide it into, under the hood, you divide it into tetrahedra,
Okay.
and then apply third order scheme, which is third order on tetrahedra. My kind of general expectations, if you have underground nice hexahedral grid, and you divide this nice hexahedral grid into tetrahedra, solution to tetrahedral grid also will be very nice.
Yes.
So
yes. That'll be an interesting comparison. Yes, yes. But
more expensive, I'm not sure. It's less expensive.
It would be astronomically expensive for the first solver. If you're doing a node-based scheme, the number of edges would go up by a factor of.
But it's opposite, because for implicit solver, your neighbors is actually all nodes of elements that surround it. Not so tetrahedral actually has much fewer elements. It's a huge reduction. The linear solver is much faster.
Really?
Yeah,
Okay.
it goes in opposite way.
Okay, I should talk about that with you. Yeah, it's interesting. It doesn't fit my intuition.
Yeah, but so like for EBV scheme, that's a kind of proven thing.
Interesting.
Much faster. So that like linear solver just have much smaller bandwidth on tetrahedral grids than on general mixed element.
Really?
Yeah.
So when you're sure, okay.
okay. Oh yeah. Okay, so Mike, you have a question?
Yeah, I have two questions. The first one I think is related to Boris's question, and that's the relationship to the third order edge-based scheme, which I think you might have partially answered. So, and then my second question is, how is a smooth hex mesh defined? Is there a mathematical limit on the metrics? Like the some properties of the mesh, or can you be more precise about what you mean by a smooth hex mesh? Thank you.
Okay. Yeah, it's a smooth hex. Maybe I should say structured mesh. Yeah. If the connectivity is irregular, now I don't know what's going to happen. But these schemes rely on grid lines. The X line, is also on the lines and equally spaced. And that way you can achieve because this is based on 1D high order algorithm. So you must have 1D structure with uniform spacing, and that's what I mean by smooth hexa.
Uniform structured grids is actually more general term, because you can have irregular structured grids. Right. Structure just means that your topology is repeated from place to place.
Yeah.
But you require also smoothness of line.
Right. Another thing is, not just the grid lines, because when I look at the triangular mesh, very nice smooth triangular mesh. I mean, just subdivide of the quad mesh. There are grid lines 1, 2, 3, but when I try this 1D analysis, okay, we rely on this property that if you apply gradient algorithm to the gradient, you get second order derivative in a certain direction. This is destroyed on triangular mesh. This is only true for Cartesian mesh, quad mesh, when you have one line and two lines. Triangular mesh, I'll try to look for some formula that would give me the 1D formula.
Come to me.
Yeah.
I'll give you as well.
Okay, that'll be interesting. Go.
I just want to make sure you're doing that question first. So, for example, in your wake case, where you showed vortex shedding off of a cylinder, it's pretty common in the grid generation community to coarsen the grid as you get closer to the outflow boundary for a number of reasons. I'm assuming in yours, you kept just a constant spacing.
No, it's coarsened towards the end. It was just a part of, I believe. No.
Okay. So then does that maintain third order accuracy if you're coarsening as you're getting closer to the outflow, or does that deteriorate?
Not exactly, because it's not a uniform spacing. Yeah, not exactly. But if you do accuracy verification, maybe you're losing third order accuracy. but I'm saying it's probably more accurate than the second order scheme.
Okay.
Yeah.
So it might not be formally third order accuracy anymore, but you still recover some of the favorable properties of the third orders.
Because having exactly third order accuracy, I don't know how important it is. The Young and Harris, the U-MUSCL, without flux reconstruction, is theoretically second order, but it's a very low dissipation scheme. So it's actually a very useful scheme. So, so that's why I'd like to see more application of these schemes, because it might turn out for some applications, maybe the flux reconstruction doesn't do much. And all you need is just to do the solution reconstruction with lower dissipation. So that might be true. So, but theoretical side, I just wanted to do it right first, and then decide which one is more suitable for practical applications. Another question from online, Sinus? Go ahead. I don't hear you.
I have a couple of questions.
Go ahead.
First one is FSR schemes. You did the reconstruction of both fluxes and the solutions, and you showed the simulation of a shoe washer test case. That means you might be limiting both the fluxes and the solution values.
Oh, that's a good point. Yes. In that case, I didn't. I mean, I did only solution limiting here because it's a QFSR. Q is this one. So if I limit solution, I'm actually limiting the flux at the same time. So it was very convenient to try out with this scheme. That's why I tried QFSR. Okay.
It won't give any oscillations because the flux is unlimited. Like it's a linear one. So I'm not sure why it didn't give any oscillations.
Limited through chain.
Yes. So what do you mean?
Usually if we do a Vino scheme, you reconstruct F plus. F plus is a F minus, both the fluxes and the solution variables will be there. So then you do your Vino scheme, you don't get any oscillations. But in your case, you're not doing anything for your fluxes. You're only limiting your solution variables, and you're still not doing any oscillations.
Yeah,
that is interesting, actually.
Yeah, Vino scheme, you adjusting your stencils, upwind. That way you actually introduce dissipation. But here, I'm just using left and right fluxes, yes, and I don't really limit the fluxes, but the flux, it depends on the solution, reconstructed solution here. You left, let me see. Okay, if I limit this solution, and then if this U left becomes UJ, then this goes to 0 and this goes to 0. So I only limit solution, and that will propagate to the flux reconstruction in this case. That's what I did. Does that answer your question? No.
Mostly. Thank you.
Mostly. You have other questions? That's all? Okay. Thank you, Sinus. And Bill?
Yeah, I just wanted to make sure I understood what you've been saying. You've been mentioning things like uniform spacing and orthogonal. Does this mean that formally these schemes are only the accuracy advertised if you're on a Cartesian mesh or not? Okay.
Yes. Yeah. But I'm saying if it's smooth and a little bit curved, but if mostly equally spaced, you get better accuracy. That's what I'm saying. Yeah.
Oh, okay, yeah. Just wanted to make sure I understood what you're saying. Thank you.
Thank you. Okay. Pedro?
So if we build a quite exactly uniform for boundary layer, like nice boundary layer type of grid.
Yes.
Your spacing is going to grow in the one normal direction.
Yes.
Maybe in the extremal direction we can keep nearly constant. Then this accuracy third, fourth order, we are going to have, how do you before running the simulation and doing a accuracy test, can we expect what's going to happen, or we need to do the test with different resolutions to see where we are going, what type of accuracy we have?
If you want to know the order of accuracy on non-uniform mesh, yes, you have to do some tests, but my guess is you don't really need to. Yeah, I would expect it's at least it's less dissipated, and it will give you more accurate solution. But that's where, I mean, this nice mesh over the wall. That's where my concern was. The boundary, near the boundary, is not high order, even for Cartesian mesh. That's why I try to develop the boundary procedure to keep all high order accuracy everywhere. Yeah, but a little bit stretching, smooth stretching, I don't think it affects very much. You might lose fourth order error convergence, but I expect it to be much more accurate than second order scheme.
So near the wall, there's still something to improve in the boundary condition.
Yes.
I think we play a little bit with those, and we didn't see much improvement for the laminar boundary layer, high speed, Mach 6 or something. But
the stretching ratio, so that like typically it's OH, like so that you use one.
Maybe it's also the boundary.
And that when you have stretching, that will limit you to second order accuracy in this direction. If you want high order accuracy, the stretching ratio should be like 1 of H P minus 1, but that it means that you basically have uniform grade.
Yeah, these schemes are kind of cheap alternatives. I mean, for non-uniform irregular mesh, if you really want high order, DG or spectral collocation schemes are available. They are available. But to implement this, a lot of work. I mean, if you have time and resource, you should do it. But if you don't, and you want to try something simple, then these schemes can be useful. And then you just put some effort generating nice mesh, and then you get better accuracy. Online, Dan, you have a question?
Yes, thank you very much for this interesting presentation. And my question is related with the previous question about the shock capturing with the flux reconstruction. And have you tried simulate some case involving strong shocks? Because usually, in my experience, if we conduct reconstruction for floods, it's usually very difficult to surprise numerical oscillations.
Sorry, what was the question?
You can try some more complicated.
More complicated cases? No.
No.
Yeah, I'd like to, but I'm an algorithm developer. I develop algorithms and I publish them and share them. And I'm hoping that people will try.
You get yarigari and suffering is less.
Yeah. So I didn't get a chance to try this myself. But now in FunCD, so I'm hoping at least the aeroacoustics group are using these schemes and they like it. So I hope that they will present results in the future conferences. Thank you for asking. Okay, Boris.
Kind of question about the first part. So that we basically have several families of high order solutions that are different from each other by h squared, right? So that depending on interpretation of the solution, you have some, I don't know, feeling recommendations of which one is more accurate if we talk about common integrated quantities, for example, we won't say like for lead, for drug, because like which interpretation may be more. That I don't know even how well to formulate the question, but kind of the question that we have different high order solutions that differ from each other by h squared, that raises kind of question.
You mean h squared?
This one is better than another.
That's a difficult question.
Yeah.
I mean, integrated quantities, when you have an error, when you integrate, some errors will cancel, upon integration. So even if you have an oscillatory viscous stresses over the wall, but if you integrate, it comes out to be right. But so I don't know.
For example, if you have two different third-order solutions, and we compute some integrated quantity, do we expect like that this integrated quantity will converge with third order for both of them, or like is it? And do we need to have different, I guess, integration, right? So that because one should take into account that we integrate cell average versus phase average.
I mean, if you have third order actually solution at the wall, then you should integrate to high order. Because otherwise, your geometry approximation is already, it's always low order to take advantage of, high order solutions. Because high order solutions means you can compute gradients to high order. You can reconstruct solution and generate more solution data points, and then you can use high order integration.
But you assume kind of that some polynomial way, okay, we can go outside.
Yes.
But I don't know how to formulate the question correctly, but basically relation between interpretations of the solution and say surface integrated quantities. So,
Okay, let's go back to the smoothing mesh. So all this Cartesian background mesh with the AMR, you showed on the picture, are they considered smoothing or not? Yeah,
it's
they have different sides.
Yeah, it's smooth in each region.
Okay, so about
the interface, but this is good.
Yeah.
I wouldn't say this is bad. I want these grid generation people, keep their jobs and then.
But you're not entirely doomed. If you did a Morton patch approach or something like that, you can recover it. You just can't use the scheme correctly. So.
Okay. Got it.
Yeah, I was going to ask so obviously the formal order of accuracy is very important, but you can also talk about the resolving power of a different scheme. So for example, you could have a fourth order central difference, but you could also have a compact scheme that gives you better resolving power at the same order of accuracy. Right. So I haven't wrapped my brain around how that sort of paradigm applies to this. Does we're moving to higher orders, does that also mean we're getting better resolving power, or?
Oh, that's an interesting question. Yeah. The resolving power is not necessarily related to the formal order of accuracy.
Yeah, correct.
Yeah, I think that ask question Sinus, he had a paper showing that low order scheme can have better resolving power. So that's also interesting point. I didn't get a chance to investigate this, but before to investigate this, it's good to have these schemes in place. And you mentioned the implicit compact scheme. Right? It's possible also to develop high order compact scheme. I mean, for unstructured grid. If the grid happens to be regular, then this reduces to those compact schemes using implicit edge-based schemes. For regular TED, it achieves fourth order accuracy. And you can apply that algorithm directly to the flux. So that's another path you can take if you want. But unlike structured grid, for unstructured grid, now you have to solve the linear system. It's not like a sweep in each direction. Now you have to solve the global linear system. But if you're interested, you can try this. Yeah, if there is an interest, I would try.
Yeah, I mean, you showed problems for the vortex convection and a couple other ones where you showed that you are getting good resolving power.
Yes.
I just wondered if there's any, because I haven't wrapped my brain around how to take that paradigm and apply it to your work. But yeah, here you do show that you do get low dissipation, you do get good resolving power.
The point of this work is I'm trying to bridge the world of structured grid algorithm and unstructured. How we can arrange this unstructured grid scheme so they become structured grid scheme when the grid is actually structured. So that's another bridge I can probably build, the compact scheme and implicit gradient scheme for unstructured. If the grid happens to be regular, yes, it achieves full order accuracy.
And this scheme have some upwinding paradigm, which like compact scheme typically purely central, so that you don't know from what side boundary layers. And so that's kind of difference and advantage, I think, this approach. Upwinding is important, kind of, to know from what side information.
Oh, still, Prahlad.
Yeah, so maybe this is related. So the second order U-MUSCL scheme, you can tune the numerical dissipation by varying kappa, right? As kappa tends to 1, the numerical dissipation goes to 0. So I was curious whether you have some similar mechanism in this higher order schemes.
Oh, yes. Yeah, the solution difference of this U-MUSCL scheme is actually third order, and for any kappa, and the kappa 1, and then you get 0 dissipation, yes. And when you do a second derivative, the higher order reconstruction, this third order error is eliminated. So the next one will be, I think, the 5th order. I think there is no 4th order. This is a mistake, I guess. So yes, you can still adjust your dissipation by changing kappa. That's why I said I used a different coefficient theta for the flux reconstruction. Theta. So you can choose, you can still adjust kappa for dissipation. So you can have 0 dissipation third order schemes, 0 dissipation 4th and 5th order schemes by adjusting. Yeah, thank you.
And I was just curious, what do you use for D, the flux reconstruction? The flux reconstruction, right? You have a D times UL minus UR. So what do you use for D?
Oh, D. I typically use row flux.
Okay.
So it's like an absolute Jacobian, but any numerical flux can be written in this form, and you can identify what the dissipation matrix is.
Right.
So, this is minus. Sorry. Yeah. Okay, Bill.
I'm just thinking about the bridge you're building to make unstructured grids be able to behave like structured grid codes when the grid is structured. I'm just wondering why not the approach of like create AV and Helios and Kestrel underneath them, where they combine solvers, where they have a Cartesian solver and they have a near body unstructured solver or something like that. Why not approach it with just, because I mean your efficiency for solving Cartesian meshes is much higher if you can just use that property of the mesh, as opposed to trying to solve it with an unstructured solver. You're way more inefficient by doing that. I'm just wondering if that bridge is maybe good in that you could have the near body solver and the off body Cartesian solver be the same scheme, so you'd have a much cleaner blend between the two at the interface. But it just seems to me like we ought to be just solving the Cartesian problem where we need Cartesian and solving the body fitted unstructured somewhere else.
Yeah, if the grid is always Cartesian, then there is a much better, more efficient implementation, JKL data structure. So what I'm doing here is I'm looking at the unstructured grid solver, and I'm hoping that some grids will be nice, and try to be ready for those grids. But if you are sure that your application will allow Cartesian mesh, this is not for you, of course. Yes, especially the dimension by dimension sweeps. That's if you can do it. That's definitely a good option.
You already answered that.
Thank you.
You already answered that because you said this is a simple approach. So what Bill said is much more difficult. You've got to implement a separate solver. So you should do that, but this is a nice step in.
Yes, and these things are already in facility. Yeah. So just try to use it and see what how it works.
And for these schemes, remind me again. Many of these schemes, like the QFSR scheme, require second derivatives. They require Hexahedral.
Yes.
Does the CFSR scheme require second derivatives, or is that
second derivative? Yes, all second derivatives.
So these are a bit more. These do require a bit more work than the edge-based third order method, which doesn't require the Hessians to be stored on that. And you're currently doing this for all the results that you showed by simply applying the least squares
twice
rather than actually forming the quadratic polynomial and solving for that.
Okay. It's applying least square twice is when I first saw this, I thought it would be a good algorithm for unstructured grids. But now I realize we are not really designing schemes for unstructured grids. We are designing for Cartesian mesh. Right? So as long as it works great on Cartesian mesh, that's what we need. And it's really interesting that this A2H Laplacian is a really important ingredient. If you replace this by 3-point finite difference formula, you lose high order accuracy, actually. It's very interesting. Okay, I guess it's past noon, so it's time. Thank you very much for coming, and thank you everyone.